Hi guys, this is the EdExcel AS level Further Maths Paper 1, which covers the core pure maths section, and this is from the June 2018 series. And before we begin the paper, let's have a quick look at the examiner's report, which summarises how people did in this paper overall. Okay, so obviously quick look at the examiner's report for this paper. It was a new paper for a new specification, so because of that, a lot of students struggled to do well in this paper. There were some questions which focused on problem solving and modelling, some questions were unstructured, and because of that, a lot of the students struggled to make significant progress in this particular paper. Some questions were okay, but the algebra skills that were required in this paper, students failed to demonstrate sufficient algebra skills. Some questions which involved modelling challenged the students greatly. So, with that being said, let's jump straight into the paper. Question 1. We have the matrix M with elements 2, 1, minus 3, 4, minus 2, 1, 3, 5, minus 2. We have to find the inverse of M, giving each element an exact form. Well, for this question, part A, we have our matrix M, which is equal to 2, 1, minus 3, 4, minus 2, 1, 3, 5, minus 2. And we can find the inverse using our calculator. The inverse matrix of M will equal, if we go to our calculator, we need to go to matrix mode. We will define matrix A with 3 rows, 3 columns, elements 2, 1, minus 3, 4, minus 2, 1, 3, 5, minus 2. Once we've defined that matrix, press AC, then press Options, click number 3 for matrix A. We wish to find the inverse of matrix A. We see for each element we have a common factor of 1 over 69, so we can factorize that 1 over 69 outside. And then for the matrix elements, we have 1, 13, 5, minus 11, minus 5, 14, minus 26, 7, and 8. So this over here is our inverse of matrix A. And now for part B, we have to solve the simultaneous equations 2x plus y minus 3z equals minus 4, 4x minus 2y plus z equals 9, 3x plus 5y minus 2z equals 5. And you'd notice over here, for the coefficients of x, y and z, we have our matrix M. So, for part B, for the simultaneous equation 2x plus y minus 3z equals minus 4, 4x minus 2y plus z equals 9, and 3x plus 5y minus 2z equals 5. We can put this in matrix form. So in matrix form, of course, we have our matrix 2, 1, minus 3, 4, minus 2, 1, 3, 5, minus 2. And if we multiply this by the vector x, y, z, of course, we'd end up with our set of equations on the left-hand side here. And this, of course, is equal to minus 4, 9, 5. So to find x, y, z, we would have to multiply both the left-hand side and the right-hand side by the inverse of m. So we have x, y, z, which is equal to the inverse of m. So let's just write this out. We have m, which we will inverse, and then we multiply this by minus 4, 9, 5. So if we work this out, if we grab our calculator, we now need to define a matrix B. So if we press options, press number 1 for define matrix, we will define matrix B, 3 rows, 1 column. The elements of matrix B would be minus 4, 9, and 5. So to find x, y, z, we have the inverse of A. So we have the inverse of A multiplied by the matrix B. We get 2, 1, 3. So having said that, we can therefore conclude x is equal to 2, y is equal to 1, z is equal to 3. And now for part C, we have to interpret the answer to part B geometrically. So for part C, what this means geometrically is this solution over here is the point where 3 planes meet. And I've tried to illustrate that over here. We've got 3 planes shown here, and then the point A where all these 3 planes meet. So if I rotate this, you can see we have 3 planes which intersect each other. They all intersect at a common point A. So in terms of the examiner's report, the first thing which stands out is that this question was generally well done, with the majority gaining full marks for part A and B, which is good. And if we have a look at what people did for part A, many correct responses, you were expected to use your calculator. Now, a few people wrote their answers as decimals, and therefore, because they wrote their answers as decimals, they were unable to gain more than 1 mark, because in the question said, give your answer in exact form. For part B, the majority of students used their inverse correctly to find the coordinates using a calculator. Some students chose a manual simultaneous equation method of solution, but this often led to errors. Now, with that being said, if you go back to the question, it's only worth 2 marks. So if you're doing a manual method to work out this simultaneous equation, then you have to think to yourself, is this really worth the number of marks for the effort I'm putting in? And others used their calculator to solve the simultaneous equations rather than take the inverse matrix approach. So what we mean by that is, if you go to your calculator and then if you go to equations and functions, simultaneous equations with 3 unknowns, you can type in your simultaneous equations here. So we have 2, 1, minus 3, minus 4, 4, minus 2, 1, 9, 3, 5, minus 2, 5. We get a solution of x equals 2, y equals 1, and z equals 3. So potentially, we could be using our calculator to solve these simultaneous equations, which is perfectly fine. But for part C, there was some confusion with the demand here. This question isn't talking about intersecting lines and it's not talking about shears of sheaths and prisms. A couple of students talked in vague terms about transformations, but they've not really clearly understood the question. Essentially, the question's talking about the point in which 3 planes are meeting, and we saw that over here. Okay? So that is essentially some of the things that you should be looking out for in this question. Question 2. We've got a cubic equation z cubed minus 3z squared plus z plus 5 equals 0. And this cubic equation has roots alpha, beta, and gamma. Without solving the equation, we have to find the cubic equation whose roots are 2 alpha plus 1, 2 beta plus 1, and 2 gamma plus 1, giving your answer in the form w cubed plus pw squared plus qw plus r equals 0, where p, q, and r are integers to be found. Well, with our cubic equation, is equal to 1, b is equal to minus 3, c is equal to 1, d is equal to 5. We can first of all find the sum of the roots, the pair sum, and the product. So we can first of all find the sum, alpha plus beta plus gamma. That will equal minus b over a. So we have minus 3 over 1, which is minus 3. We can now find out the pair sum. We have alpha beta plus beta gamma plus alpha gamma. This is equal to c over a. So we have c, which is 1, over a, which is 1. The pair sum is 1. We can find the product, alpha beta gamma. That will equal minus d over a. So we have minus 5 over 1, which is minus 5. So knowing the values of the sum, the pair sum, and the product, we can now find the sum with these roots, the pair sum with these roots, and the product with these roots. So if we consider the sum will equal 2 alpha plus 1 plus 2 beta plus 1 plus 2 gamma plus 1. We can simplify this as 2 lots of alpha plus beta plus gamma plus 3. Alpha plus beta plus gamma, we said that was minus 3. Sorry, that's equal to 3. So we have 2 lots of 3 plus 3, which is 9. We can now find the pair sum. So, for the pair sum, we have 2 alpha plus 1 lots of 2 beta plus 1 plus 2 alpha plus 1 lots of 2 gamma plus 1 plus 2 beta plus 1 lots of 2 gamma plus 1. So, working this out, 2 alpha times by 2 beta, that's 4 alpha beta. 2 alpha times by 1, that's 2 alpha. 1 times by 2 beta, that's 2 beta. 1 times by 1, that's 1. 2 alpha times 2 gamma, that's 4 alpha gamma. 2 alpha times by 1, that's 2 alpha. 1 times by 2 gamma, that's 2 gamma. 1 times by 1, that's 1. 2 beta times by 2 gamma, that's 4 beta gamma. 2 beta times by 1, that's 2 beta. 1 times by 2 gamma, that's 2 gamma. 1 times by 1, that's 1. And if we collect like terms, you'd notice we have 4 lots of alpha beta plus beta gamma plus alpha gamma plus 4 lots of alpha plus beta plus gamma plus 3. The pair sum, that was 1. The sum, that was 3. So we have 4 lots of 1 plus 4 lots of 3 plus 3. That's 19. We can now work out the product. For the product, we have 2 alpha plus 1 lots of 2 beta plus 1 lots of 2 gamma plus 1. Let's first of all multiply the 2 beta plus 1 and the 2 gamma plus 1 together. 2 beta times by 2 gamma, that's 4 beta gamma. 2 beta times by 1, that's 2 beta. 1 times by 2 gamma, that's 2 gamma. 1 times by 1, that's 1. If we expand this out, 2 alpha times by 4 beta gamma, that's 8 alpha beta gamma. 2 alpha times by 2 beta, that's 4 alpha beta. 2 gamma times by 2 alpha, that's 4 alpha gamma. 2 alpha times by 1, that's 2 alpha. 1 times by 4 beta, that's 1 times by 4 beta gamma, that's 4 beta gamma. 1 times by 2 beta, that's 2 beta. 1 times by 2 gamma, that would be 2 gamma. 1 times by 1, that would be 1. And if we simplify all this, we have 8 lots of alpha beta gamma plus 4 lots of alpha beta plus beta gamma plus alpha gamma plus 2 lots of alpha plus beta plus gamma plus 1. We have 8 lots of minus 5 plus 4 lots of 1 plus 2 lots of 3 plus 1. The result of this is minus 29. So knowing the pair sum, the product, knowing the sum, the pair sum, and the product, we can therefore conclude we have a new cubic equation, w cubed minus 9w squared plus 19w plus 29 equals 0. So, examiner report wise, this question was a new topic on the specification, though use of the sum and product of roots has been on the international A-level specification, but these specimen papers will have been the only previous examples some will have seen. Now, in terms of how students did in this question, most students used the main approach to answer this question, and this seemed to be the most effective method. So in terms of the mark scheme, I think that's referring to this first method over here. And what else can be said? The question was answered really well. The main errors were basically algebra problems, so that's algebraic manipulation. And interestingly, this has really evidenced the need for students studying maths at this level to be competent with algebraic manipulation. And there were a number of students who confused their variables through most managed to correct this at the end. The alternative method, which is the method I used, that gave more problems, interestingly, right? And this style of answer may be more familiar than the linear transformation, and so in time students may learn the best approach to this type of question. Many students use b over a and d over a instead of minus b over a and minus d over a. So with my method, that's referring to basically this bit over here. And again, there were algebraic manipulation problems. And omitting the equals 0 and hence losing the final answer mark was rare. So what that means is basically make sure you include an equals 0. Question 3, part A. We have to shade on an Argand diagram the set of points where mod of z minus 1 minus I is less than or equal to 3 and the argument of z minus 2 is greater or equal to pi over 4 but less than or equal to 3 pi over 4. And before we attempt such a question, we can rewrite this bit over here. For a set of complex numbers, we can rewrite z minus 1 minus I as z minus 1 plus I. And this is obviously less than or equal to 3. And then for our second one, for a set of complex numbers where we have the argument of z minus 2 being greater than pi over 4 but less than or equal to 3 pi over 4, we will notice over here we have a circle with center 1, 1 and radius 3, and here we have a half line. So we have a half line from the point to 0. Okay, so the next thing we need to do is first of all draw this circle, which I will do now. So having drawn the circle with radius 3, center 1, 1, Let's now draw the half line from the point 2, 0, which is over here. The first thing we need to do is, well, over here we have essentially a V shape. So in between these two angles we have 3 pi over 4 take away pi over 4, which is a half pi, 90 degrees. So we have a V shape, and we want the argument to be greater or equal to pi over 4. So that's anything above the line pi over 4, but less than or equal to 3 pi over 4. So we have first of all our line 3 pi over 4. Remember, we go anti-clockwise. So 3 pi over 4, that's over here. Okay, let's just add this on. We have 3 pi over 4. And then we have this line over here, which is pi over 4. And first of all, if we consider the circle, we want the circle to be less than or equal to 3. So that includes everything within the circle. And for the next bit, where the argument is greater than pi over 4, but less than 3 pi over 4, that region is essentially everything enclosed within here. And that's including the criteria for the circle. So the region we want is this region over here. Okay, so let's just finish marking these points on. This is the region which we require. And now for part B, the complex number w satisfies mod of w minus 1 minus I equals 3, and the argument of w minus 2 equals pi over 4. We have to find, in simplest form, the exact value of the norm of w squared. We can do that by Pythagoras. Essentially, we can first of all find the intersection point between this and this, which will be this point over here. And we can then use Pythagoras to work out this w squared. Okay, so I'll just make that a bit clearer. Here we have w. Okay, so we will at some point have to use Pythagoras to find out what norm of w squared is. But before that, we need to find this intersection point over here. And because we have pi over 4, we can think of this red line to be equivalent to x minus y. We can think of this line to be the same as y equals x minus 2. Okay, so let's just write all that down. So in equivalent Cartesian form, we have x minus 1 all squared plus y minus 1 all squared equals 9. That's the equation of the circle. And then we have y equals x minus 2. That's this line over here, the pi over 4. If we solve equation 1 and 2 simultaneously, we can substitute in for this y x minus 2. So we have x minus 1 squared plus x minus 2 minus 1 squared equals 9. So we have x minus 1 squared plus x minus 3 squared equals 9. If we expand and simplify, we have x squared minus 2x plus 1 plus x squared minus 6x plus 9 equals 9. Simplify that a bit more. We have 2x squared minus 8x plus 1 equals 0. And then we can use the quadratic formula to solve this equation. X equals minus 8 plus minus 8 squared minus 4ac all over 2a. Okay, and if we work this out, so let's just grab our calculator. If we go to menu, equation, we have a polynomial of degree 2 with coefficients 2, minus 8 and 1. We have 4 plus root 14 over 2 and 4 minus root 14 over 2. So we have 4 plus minus root 14 over 2. And now that we know the value of x, let's rewrite that as 2 plus root 14 over 2. So therefore x equals 2, the reason we have 4 over 2, which is 2, plus minus root 14 over 2. Of course, if you go back to the diagram, we want just the positive solution. The reason we want the positive solution rather than the negative solution's over here. We just want the positive solution. Sorry, the negative solution would be over here somewhere. Okay? So we just want the positive solution, and we know what the equation for y is. That would be, if I get rid of this, that would be x minus 2. So we can conclude y is equal to 2 plus root 14 over 2 minus 2, which is root 14 over 2. So if we add this to the diagram, here we have 2 plus root 14 over 2, and here we have root 14 over 2. We can now use Pythagoras. So, using Pythagoras, we have the norm of w squared equals 2 plus root 14 over 2 squared plus root 14 over 2 squared. So if we work this out, the norm of w squared, we have 2 plus root 14 over 2 squared plus root 14 over 2 squared, which is 11 plus 2 root 14. So we have 11 plus 2 root 14 as our final answer. So, examiner report wise, first thing for part A, obviously most students manage to draw a circle with centre 1 plus I, or in equivalent form, a circle with the centre 1, 1. a lot of people realize that a V-shape must have been drawn, but the problem with some V-shapes is more to do with where the V-shape starts. So if I go back to the diagram, it should be over here. And also the shape of the V. Remember, we want this sort of 90 degrees in between the V's. If I just add that over here, we want 90 degrees in between the V's, because the difference between 3 pi over 4 and pi over 4 is pi over 2, which is 90 degrees. But irrespective of that, a lot of students realized the correct area that was required was the bit in blue, which I shaded over here. For part B, that was more challenging. If we remind ourselves of what part B was, that was finding the norm of W squared. And the reason that was challenging is because many students did not know where to start. So a lot of people failed to realize that we'd have to use Pythagoras and solve simultaneous equations. There were some students who gave the equation of the circle and the half line and then solved those simultaneous equations correctly. Some students tried to work with the diagram and find the point of intersection by simple trigonometry, but often made false assumptions when doing so. A few considered the triangle with vertices at 2, 0, the center of the circle, and the point of intersection, correctly calculating the sides as root 2, 3, and root 7. They were then able to get the point of intersection from trigonometry. A few students left their answer as a decimal rather than a surd. If we go back to the question, in terms of decimals, remember the question says exact value, but the key in this question is to recognize that we want to find an intersection point. And then we can use, for example, Pythagoras to find the value of the norm of W squared. Question 4. Part of the mains water system for a housing estate consists of water pipes buried beneath the ground surface. The water pipes are modelled as straight line segments. One water pipe W is buried beneath a particular road with respect to a fixed origin. The road surface is modelled as a plane with equation 3x minus 5y minus 18z equals 7, and W passes through the points A with coordinates minus 1, minus 1, minus 3, and B with coordinates 1, 2, minus 3. The units are in meters. We have to use the model to calculate the acute angle between W and the road surface. So I've drawn over here a diagram. We've got our plane pi, and we've also got our line W, and we've got the points A and B. Now, we already know that the equation of the plane is given by, let's write this down, 3x minus 5y minus 18z equals 7. And if we were to put that in equivalent vector form, we have r dot product with the normal, 3 minus 5 minus 18, and this is equal to 7. Now, the first thing we can do, we can find the direction of W by considering the vector AB. So the vector AB, that's equal to the vector OB minus the vector OA. So the vector OB, 1, 2, minus 3. The vector OA, minus 1, minus 1, minus 3. Working this out, we get 2, 3, 0. So that's the vector AB. And therefore, the acute angle, that will be given by sine theta equals the modulus of B dot product with n over the magnitude of B times by the magnitude of n. So what we need to do in this question then is work out B dot n and the magnitude of B times the magnitude of n. Now when we say B over here, that refers to the vector AB. So if we work that out, remember the normal vector is 3 minus 5 minus 18. So if I actually draw all this on, we have the vector little b over here, which we'll show over here. And then we've got our normal vector to the plane. We'll do this in a different colour. That's shown over here. So if we work all this out, we have b dot n. So we have 2i plus 3j plus 0k dot product with 3i minus 5j minus 18k. And then the magnitude of b, we have 2 squared plus 3 squared plus 0 squared, square rooted, multiplied by 3 squared plus minus 5 squared plus minus 18 squared, square rooted. So we need to work this out. So first of all, working out the dot product, we have 2 times by 3 plus 3 times by minus 5 plus 0 times by minus 18. And we divide this result by 2 squared plus 3 squared plus 0 squared, that's 13. So we have the square root of 13. And then 3 squared plus 5 squared plus 18 squared, that's 358. So we need to find out the magnitude of all this. So we have 6 minus 15, which is minus 9. So we have the magnitude of minus 9 over root 13 times by root 358. So sine theta, therefore, if we work all this out, we have the absolute value of minus 9 over root 13 times by root 358. We get 0.131. And therefore, the acute angle theta is equal to the inverse sine of this, which is 0.13 radians. Of course, you can leave your answer in degrees. If you were to leave your answer in degrees, you'd get 7.58 degrees. Now for part B, a point C with coordinates -1, -2, 0 lies on the road. A section of water pipe needs to be connected to W from C. Using the model, we have to find to the nearest centimetre the shortest length of the pipe needed to connect C to W. Well, let's suppose the point C is over here somewhere. The shortest distance will be the perpendicular distance to W. as shown over here. So we can first of all find a general equation for W, and then we can find the vector CW in terms of a parameter, and then we will have to dot product that with this direction vector B. Once we've done that, we'd find an equation in terms of mu, but then sub that back in to our vector CW to find from that we'll find the vector CW, and then we can take the distance of that. So first of all, for part B, the line W has equation R equals, we have a general point -1, -1, -3, plus lambda, lots of 2, 3, 0. So hopefully that makes sense. R is equal to OA plus lambda lots of this direction vector. And we also know that CW is perpendicular to AB. So the vector CW is perpendicular to the vector AB. So we can first of all find the vector CW. We know the coordinates of C. That was given to us as -1, -2, 0. So therefore, CW is equal to OW minus OC. So we have OW, which is given by -1, -1, -3, plus lambda, lots of 2, 3, 0. And then we subtract off -1, -2, 0. We can of course conclude the vector CW is equal to 2 mu, 2 lambda, 3 lambda plus 1 minus 3. And if we know that CW is perpendicular to AB, remember AB is given by this direction vector 2, 3, 0, dot producting those together and setting that dot product equal to 0, we have 2 lambda, 3 lambda plus 1 minus 3, dot product with 2, 3, 0. Of course, this is all equal to 0. So we have 2 lots of 2 mu, so I don't know why I'm saying mu, 2 lambda plus 3 lots of 3 lambda plus 1 plus 0 lots of minus 3. And all this is equal to 0. So we have 4 lambda plus 9 lambda plus 3 equals 0. 13 lambda is equal to minus 3. Lambda is equal to minus 3 over 13. Having said that, we can now find CW. So CW will therefore equal 2 times by minus 3 over 13, 3 times by minus 3 over 13 plus 1 minus 3. So we have minus 6 over 13, 4 over 13, and minus 3. Hence we can find out the shortest distance CW by taking the magnitude of CW. So the magnitude of CW will equal minus 6 over 13 squared plus 4 over 13 squared plus minus 3 squared, and this is square rooted. So if we work this out, we have the square root of minus 6 over 13 squared plus 4 over 13 squared plus minus 3 squared. We get a value of 11 root 13 over 3, which is 3.05 meters. And therefore, that in centimeters, we can conclude that the shortest distance, so the shortest distance is 305 centimeters. And if I show you what's actually going on, we've got our plane shown here. If I get rid of the axis, we've got our point C over here, and we've got our line W over here and our vector AB. And if I vary lambda, the value of minus 3 over 13, that's 0.23. So 0.23, that's approximately 0.2. So essentially, we're finding out the distance from here to here. And we've got our equation for R shown over here. Okay? With the value of lambda equaling 0.2. So that's essentially all that's going on. Okay? Report-wise, we see that most students appreciated the strategy needed to solve the problem, and they used the scalar product to find the angle between the normal vector and the direction vector of W. And that direction vector of W, we call that little b. But many students could not find the required acute angle. A clear diagram would have helped them to visualize which angle was required. You don't even need a diagram to figure out the acute angle. If you know the formula to work out the acute angle over here, you can also do it like that. Let's see what else has been said. A common error was to subtract the result of their inverse cosine from 180. Remember, we want the acute angle. Those using sine were usually more successful. I think this formula is actually in the textbook, so stick with this textbook formula over here. What else has been said? A few found the correct angle but failed to give it to the correct accuracy or to indicate degrees or radians, and hence lost the final mark. That's actually quite surprising. You'd also have to give the units of the angle, which I've done over here. For part B, the majority of students performed the correct parametric equations for W, but many did not then find CW, and some were attempting to find a scalar product with a direction vector perpendicular to the plane. We don't want to do that. We want to find the perpendicular from the point C to W. What else was said? There were often errors with signs for those who were looking with the appropriate vectors. Those with the correct CW were usually then able to accurately use Pythagoras' theorem to gain full marks here, but they were in a minority. Fair enough. In terms of what else has been said, some of the students who correctly found the value of their parameter, lambda in our case, substituted this into the equation of line W and found the magnitude of this vector rather than finding the vector CW and its magnitude. So we found CW and then its magnitude. And those students who produced a diagram of the situation were more successful. It is perhaps a pity that a number, having done fully correct work, lost the final mark as they either failed to include units or through that the units were centimeters throughout. So there's been mention of units in this question, and with vector questions, they've pointed out that drawing a diagram would help to visualize what's going on. And essentially at some point, W will intersect the plane pi, as I've shown over here. So eventually, if we extend this plane out, eventually the plane will intersect the line L. Question number 5. We have a matrix A with elements -1/2, minus √3/2, √3/2, and -1/2. We have to describe fully the single geometrical transformation U represented by the matrix A. And if we go to our formula book, the formula we require is this one over here, where we have an anti-clockwise rotation through theta about O. And we can use that to compare our matrix A, and I'll write our matrix A here. The matrix we have is -1/2 √3/2 minus √3/2 and -1/2. We can use that to find the angle theta. And we can do that by comparing cosine theta with -1/2 and sine theta with √3/2. So for part A, using that, we have cos theta equals -1/2 and sine theta equals √3/2. We can now find the angle theta. If we work out sine theta over cos theta, sine theta, that's √3/2, cos theta, that's -1/2. So therefore, tan theta is equal to -√3. And therefore, theta will equal the inverse tan of -√3, which is -π/3. But we have to add on a value of pi as well, because we're going anti-clockwise. And we want to make sure we're in the right quadrant. So therefore, theta is equal to 2π/3. We can therefore say, we have theta in radians, we can therefore conclude that we have a rotation by 2π/3 radians anti-clockwise about O. Okay. Now for part B, the transformation V represented by the 2x2 matrix B is a reflection in the line y equals -x. We have to write down the matrix B. That's quite easy. When we have a reflection in the line y equals x, so a reflection in the line y equals -x, that will be given by 0, -1, -1, 0. Now for part C, given that U followed by V is the transformation T, which is represented by the matrix C, we have to find the matrix C. Now, we have U followed by V, So we have a rotation followed by a reflection. When we come to work out the transformation matrix, we have to work backwards. So the transformation matrix, we'd have to work backwards. In other words, we'd have to do the reflection first, followed by the rotation. So we have over here our reflection 0, -1, -1, 0, followed by our rotation -1/2 √3/2 minus √3/2 and -1/2. Working this matrix out, we have 0 times by -1/2 plus -1 lots of √3/2. For our element here, we have 0 times by -√3 plus -1 lots of -1/2. For the bottom element over here, we have -1 lots of -1/2 plus 0 lots of √3/2. And finally, we have -1 times by -√3/2 plus 0 lots of -1/2. We can of course conclude that our matrix C, which is what we want, that's equal to -√3/2, 1/2, 1/2, and √3/2. And now for part D, we have to show that there is a real number k for which the point 1k is invariant under T. Well, we have the following to say about that. So the points on the line y equals -x are invariant points, and the lines y equals -x and y equals x plus k for any value of k are invariant lines. The invariant points do not change under the transformation. In other words, if we've got a matrix transformation represented by A, B, C, D, and we've got some point x, y, because the points don't change under the transformation, we'd still end up with x, y when we apply this transformation matrix. So what that means for us then is we have our matrix -√3/2, 1/2, 1/2, and √3/2, and we've got this point 1k. When we apply this transformation, the point does not change, so we'll still end up with 1k. And what we have to do in this question is show that there is a real value of k. So essentially, we need to find a value of k for this over here. So if we multiply the matrix together, we have -√3/2, lots of 1, plus 1/2, lots of k, and then we have 1/2 lots of 1, plus √3/2, lots of k. Okay, and this is equal to 1k. So on the top, we have minus root 3 over 2 plus a half k. On the bottom we have a half plus root 3 over 2 k, and this is equal to 1 k. So we've got two equations if we compare the components. We have our first equation, minus root 3 over 2 plus a half k equals 1. We've got our second equation, a half plus root 3 over 2k equals k. We'll call this equation 2. If we solve equation 1 and equation 2 and we end up with the same value of k, we can therefore conclude that we have a real value of k, if we do indeed get a real value of k. So if we solve equation 1, we have, if we subtract a half k, well, if we add 1 to root 3 over 2, we have a half k equals 2 plus root 3 over 2, and you can try that on your calculator, from which we see if we multiply by 2, k is equal to 2 plus root 3, and if we solve equation 2, subtracting 1 from both sides, we have minus 2 plus root 3 over 2k equals minus a half, and if again multiply through by minus 2 here, k is equal to 2 plus root 3. And therefore, because we have the same value of k, we can conclude overall, because of that consistency, k is equal to 2 plus root 3, which is real. Examiner report wise, parts A, B and C should have been routine procedures, and it was surprising how many students made mistakes in these parts. I never knew that. In part A, the majority of students realised that the transformation was a rotation but struggled with the angle, whilst many students failed to mention that the rotation was about the origin. And that's surprising because it's in the formula book. A significant number also lost all 3 marks by attempting to describe a composite transformation. Part B provided mixed responses. Many did state the correct matrix, but a variety of incorrect matrices were also seen, the entries on the wrong diagonals being the most common. So if I go back here, that's just on about the diagonals here. The use of a sketch would have been advised to help trace where the coordinates 1, 0 and 0, 1 map under the transformation, and help to establish the required matrix. So what this paragraph is basically saying is, if you have your points 1, 0 and 0, 1, and then apply a transformation, you can see where the new coordinates go after a transformation and then derive a matrix from there. But I think it's a standard result to know that a reflection in the line y equals minus x is given by this. Then for part C, many students did manage to get full marks in C due to follow-through marks. However, there were a surprising number who mixed up the order of matrix multiplication and hence gained no marks. So when you deal with combinations of matrices, you have to work backwards, as I said in the question. And part D on the whole was well attempted, with only the final mark causing some difficulty. Most students that attempted part D managed to achieve a method mark and a follow-through accuracy mark, although errors in B or C prevented them getting any further. Students that had gained full marks in B and C were often students that had gained full marks in B and C often went on to get the next accuracy mark for finding a correct value of k, but not many went on to use a second equation to confirm this, thus losing the final b mark. So essentially, what this is saying is over here is just because from equation 1 we found a value of k, you have to verify that we get the same value of k when we solve the second equation. So when there's this sort of consistency, then we can conclude we've got a value of k. Question number 6. Part A. We have to use the standard results for the sum from r equals 1 to n of r squared and the sum from r equals 1 to n of r to show that the sum from r equals 1 to n of 3r minus 2 all squared is equal to half n lots of 6n squared minus 3n minus 1 for all positive integers n. So, first of all, part A, we've got this 3r minus 2 squared, and this is equivalent to 9r squared minus 12r plus 4. So we can conclude over here that the sum from r equals 1 to n of 9r squared minus 12r plus 4 is what we want to work out. And this is equivalent to 9 lots of the sum from r equals 1 to n of r squared minus 12 lots of the sum from r equals 1 to n of r plus 4 lots of the sum from r equals 1 to n of 1. And the sum from r equals 1 to n of r squared that's in the formula book, I've highlighted it over here. That's a sixth n lots of n plus 1 lots of 2n plus 1. So let's just write that down. We have 9 times by a sixth n lots of n plus 1 lots of 2n plus 1, and then we have minus 12 lots of the sum from r equals 1 to n of r. You should know by heart that's a half n lots of n plus 1, and then we have 4n. So we have 9 over 6, which is 3 over 2. So we have 3 over 2 lots of n lots of n plus 1 lots of 2n plus 1 minus 6n, because 12 times by half, that's 6. So we have 6n lots of n plus 1. And then we still have this 4n. We can factorize out a half. And the reason we can factorize out a half, if we look back, we have a half here. And then we can also factorize out the n. So factorizing out a half n, inside this big bracket we have 3 lots of n plus 1 lots of 2n plus 1. Then we have minus 12 lots of n plus 1, because 12 times by minus a half n gives us 6n. And then we have plus 8, because a half n times by 8 gives 4n. We can now simplify this big bracket. So we have a half n lots of 3 lots of 2n squared plus 3n plus 1 minus 12n minus 12 plus 8. And if we multiply the 3 into this bracket, we have a half n lots of 6n squared plus 9n plus 3 minus 12n minus 12 plus 8, which of course simplifies to a half n lots of 6n squared minus 3n minus 1. Okay, now for part B, hence find any values of n for which the sum from r equals 5 to n of 3r minus 2 all squared plus 103 lots of the sum from r equals 1 to 28 of r cos r pi over 2 equals 3n cubed. Okay, so I've written out the question as two separate parts. We first of all have to deal with the bit in red. That's the sum from r equals 5 to n of 3n minus 2 all squared. And the bit in blue, that's 103 lots of the sum from r equals 1 to 28 of r cos of r pi over 2. So, if we consider the bit in red, then what we have over here is we can rewrite this entire thing as the sum from r equals 1 to n of 3n minus 2 squared minus the first 4 terms. Okay, so you should be familiar with why I'm doing this. And we also have the bit in blue, which is 103 lots of r equals, the sum from r equals 1 to 28 of r cos of r pi over 2. And obviously this is equal to 3n cubed. So we know the sum from r equals 1 to n of 3n minus 2 all squared. We literally just worked that out. We found that to be a half n lots of 6n squared minus 3n minus 1. And then we subtract off the sum from r equals, the sum from r equals 1 to 4 of this thing. So we substitute in 4 over here. So we have a half times by 4 times by 6 times by 4 squared minus 3 times by 4 minus 1. And then we add on 103 lots of this split in blue. Now, when r equals 1, we have 0, because then we have cos of pi over 2, which is 0. And then when r equals 2, we end up with minus 2. When r equals 3, we have 0. When r equals 4, we have 4. When r equals 5, now essentially if I get a calculator, it might make it easy to understand. So what we have over here is 1 lots of cos of 1 pi over 2, which is 0. Then when r equals 2, we have minus 2. Then when r equals 3, we have 0. When r equals 4, we have 4. Now, when r equals 5, we have over here 0. When r equals 6, we have minus 6. When r equals 7, we have 0. When r equals 8, we have 8. And you'd begin to notice a pattern. The pattern is, if I continue to work this out, when r equals 9, we have 0. When r equals 10, we have minus 10. when r equals 11, we have 0. And then when r equals 12, we have 12. And we can carry on, but the final two terms, well, the final four terms will be 0 minus 26 plus 0 plus 28. And the reason for this is because we have 0 minus 2 plus 0 plus 4. We have a pattern emerging. And every 4, we have a difference of 2. So, let me just write this down. What's essentially happening is every 4, there's a difference of 2. So here there's a difference of 2. Here there's a difference of 2. Here there's a difference of 2. And for the last terms, there's a difference of 2. So we have 4 sets repeating themselves 7 times, because 4 times by 7 is 28. So over here, we have 2 being added to itself 7 times. So we have over here then a half n lots of 6n squared minus 3n minus 1 minus the 166, just to emphasize where the 166 came from. That was just working out this bit over here. And then we have 103 lots of, we have 103 lots of 2 times by 7. Okay, and obviously this is equal to 3n cubed. And if we simplify all this, multiplying the half n into the bracket, we have 3n cubed minus 3 over 2 n squared minus a half n minus 166 plus 103 times by 14, so which is plus 1442 equals 3n cubed. And first of all, the 3n cubes cancel on both sides, so let's just cross those up. And then if we do a bit of algebra, we'd end up with minus 3 over 2 n squared plus a half n minus 1276 equals 0. Multiplying through by minus 2, we end up with 3n squared is 2552, and this is equal to 0. We can now use the quadratic formula, so n is equal to minus 1 plus minus 1 squared minus 4 lots of 3 lots of minus 2, 552. This is square rooted. Then we divide through by 2 lots of 3. So we can find the values of n. So if we go to our equation, we have a polynomial of degree 2 with coefficients 3, 1, minus 2, 5, 5, 2. We end up with 29 and minus 88 over 3. So we have n equals minus 88 over 3 and 29. N is equal to 29, which is our final answer. Examiner report wise, part A, many students achieved full marks in this part, which is good. Those who did not often made mistakes in the initial expansion of the bracket, with 3r minus 2 squared as seen as 9r squared minus 6r plus 4 a significant number of times. Sometimes the solutions were made far more complex than necessary as students chose to multiply the bracket the bracketed expressions out before factorization rather than looking for a common factor first. So what they are saying over here is the common factor was a half n. And if you recognize that, that would make your life much easier. In terms of what else was said, there were some attempts at proof by induction, which in the context of this question generally gained no marks. Okay. But part B was less successful for many students. Some substituted n equals 4 unsubtracted to achieve the first method mark, but a few substituted n equals 5 and many did not seem to have noticed the lower limit. So essentially that's on about this bit over here. And what else can be said? The summation of the cosine term caused problems for the majority of students. It was rare to see solutions where the terms of the cosine sum were written out so that students could appreciate the sequence generated. It seemed as though students were determined to use a standard formula to add up these terms rather than look up at the problem in a simpler way. And not all students had the equals 3n cubed, and so never eliminated the cubic term to achieve a 3-term quadratic. Those that had a 3-term quadratic were usually able to earn a method mark for solving it. Of those with the correct solutions, most correctly identified n equals 29 as the final answer. Now, if you actually consider this bit over here, if I grab my calculator, if we attempt to work out that sum, 103, lots of the sum of x times by the cosine of x pi over 2 from r equals 1 to 28, close this bracket, you get a syntax error, so you can't even use a calculator in this question. So I think the way I set this out makes complete sense, and essentially you have to notice every 4 terms you have a sum of 2. Question 7. F of z equals z cubed plus z squared plus pz plus q, where p and q are real constants. The equation f of z equals 0 has roots z1, z2 and z3. When plotted on an Argand diagram, the points representing z1, z2 and z3 from the vertices of the triangle form the vertices of a triangle of area 35. Given that z1 equals 3, we have to find the values of p and q. Well, if z1 equals 3, we know z1 is a root, so z equals 3 is a root of f of z equals 0, and because of that, through the factor theorem, we can work out the value of f of 3 equals 0. So through the factor theorem, we have f of 3 equals 0, so we have 3 cubed plus 3 squared plus p lots of 3 plus q equals 0, which we can simplify. 3p plus q equals minus 36. And because of that, we can therefore conclude that z minus 3 is a linear factor of f of z. Okay, now you may know from your regular A-level maths that a linear factor multiplied by a quadratic factor gives a cubic. So therefore we can factorize f of z as the product of a linear factor and a quadratic factor. Okay. So having said that, I mean, this question is quite complicated in of itself, but we'll do this as best as we can. We have z minus 3, our linear factor, multiplied by some quadratic, z squared plus az plus b. And if we multiply our linear by our quadratic, we end up with a cubic. Our cubic in this case is z cubed plus z squared plus pz plus q. We can find out the values of a and b in terms of p and q by comparing coefficients. So now compare coefficients. And if we do so, if we compare the z squared, on the left hand side, if I grab a different colour, z times by az gives a z squared term. If you compare the z squareds, we have a, lots of them, and then we have minus 3 lots of z squared. So we have a minus 3. And on the other side, we have one of them. Of course, a is equal to 4. So let's just write this in black. A is equal to 4. Now, if we compare the z terms, let's do this in a different colour. If we compare the z terms, we have z times by b, so we have b, and then we have minus 3 lots of a of them, and on the other side we have p of them. We know that a is equal to 4, so we have b minus 3 times by 4, which is 12. This is equal to p. We can therefore conclude b is equal to p plus 12. Okay, so a is equal to 4, so 3 times by 4, that's minus 12. So therefore b is equal to p plus 12. And if we compare the numbers, we'll do this in orange. On the left hand side we have minus 3 times by b of them, so we have minus 3b. And on the other side we have q of them. We'll leave that as it is. So knowing the values of a and b, if we replace a with 4 and b with p plus 12, we can therefore conclude that f of z equals z minus 3 multiplied by z squared plus 4z plus p plus 12. And if we solve f of z equals 0, we know that z equals 3 is a solution. So let's just write that down. If we solve f of z equals 0, the quadratic factor, has roots which form a complex conjugate. Conjugate. And the reason they form a complex conjugate is, if we go back to the diagram, we were told that we can plot the roots on an argon diagram. So we're expecting that we have complex roots when we solve this quadratic. So we know what Z1 and Z2 are. So sorry, we know what Z1 is, that's 3. So Z2, 3 will be of the form x plus minus iy. So hopefully that makes sense. So what can we say from here? Our quadratic factor z squared plus 4z plus p plus 12 equals 0. This would have roots of z equals x plus minus iy. And if we use the sum of the roots and the product of the roots for a quadratic, first of all, you'll notice, we'll do this in a different colour. A is equal to 1, B is equal to 4, C is equal to P plus 12. The sum of the roots, that will equal alpha plus beta, and this is equal to minus B over A. So we have minus B, so we have minus 4 over A, which is 1. So that's minus 4. So alpha plus beta, our two roots, we have x plus iy plus x minus iy equals minus 4. Okay, so alpha and beta are x plus iy and x minus iy respectively. So we see over here that 2x is equal to minus 4, and therefore x is equal to minus 2. So what does this mean? Well, it means that z23 will be of the form minus 2 plus minus iy. And if we consider the product of our roots, the product is equal to alpha beta. So alpha beta is equal to c over a. C is given as p plus 12. A is equal to 1. So c over a is p plus 12 over 1, which is p plus 12. We might use this later on. So it would help now if we draw our roots on an argon diagram. So now draw roots on an argon diagram. So this is where the complication lies. If we draw a quick argon diagram, which I will do now. So if I just draw a quick argon diagram, we have something which looks like this. Okay, so we have our real axis and our imaginary axis. So we already know that we have a real root of x equals of z equals 3. So if we sketch that on our argon diagram, we have 3 over here. Okay, so this is 3. And our other two roots, that's minus 2 plus iy, minus 2 minus iy. So that will look something like this. If I draw it on, we have our other roots shown here. So we have minus 2y. Here we have minus 2 minus y. Okay? So having said that, we can now draw a, well, we know that the area, well, if I go back to the question and give you the exact wording, we know that when plotted on an arcing diagram, which we've already drawn, the points representing Z1, Z2 and Z3 form the vertices of a triangle of area 35. So with this, we know that the area of a triangle is equal to 35. So let's just write this down. We know the area of the triangle is 35. So let's have a quick sketch of a triangle. We have this base over here multiplied by the height over here. Now we know that the base of the triangle, we're going from y to minus y, so that would be a length of 2y. So let's just add this to the diagram. We have 2y over here, and the height of the triangle is, well, we're going from minus 2 to 3, so the height is 5. So we know that the area of the triangle is 35. So we have a half times by the base 2y times by the height 5. This is equal to 35. Y is equal to 7. So knowing that y is equal to 7, we can therefore conclude that Z23 is equal to minus 2 plus minus 7i. Hence, what we can now do is find the values of P and Q quite easily. We know already that alpha times by beta is equal to P plus 12. We know alpha and beta are minus 2 plus 7i and minus 2 minus 7i respectively. So using the product, we can therefore say that we have minus 2 plus 7i, lots of minus 2 minus 7i, so alpha times by beta equals P plus 12. So we have 53 equals P plus 12. P is equal to 41. And we also know that minus 3b is equal to Q. We said that before over here. And we also know that B is equal to P plus 12. So we know that minus 3b is equal to Q and that B is equal to P plus 12. So if we substitute in P into here, we can find out the value of B and then we can find out the value of Q. So we have minus 3b, so we have minus 3 lots of P plus 12 equals Q. So we have minus 3 lots of 41, that's P, plus 12. This is equal to Q. Q is equal to minus 159. We know the values of P and Q, and therefore f of z is equal to z cubed plus z squared plus 41z minus 159. So examiner report wise, this question 7 proved to be a very challenging question, and a significant number of blank or very low scoring attempts were seen. Many students produced work worthy of the first mark. Many achieved it several times over, but failed to make progress beyond this. either going around in circles or making wild assumptions. So I'm guessing what they mean by the first mark, if we jump to the mark scheme. I think they're just either on about stating that we have complex roots of this form, or our quadratic factors of this form, or using the factor theorem of this form. Yeah, pretty much so. What else has been said? Most recognized that an equation could be formed in terms of the area of the triangle, but the bigger challenge was to find another way into the question, i.e., by using the sum of roots, or occasionally by dividing the polynomial by z minus 3, although very few recognized that they could solve the quadratic and hence find the other two roots. So what we've done over here, when we form a quadratic, is totally legit, and then we can use the sum of the roots and the product of roots to basically form the area of the triangle, which we did towards the end of the question. Most successful students realized that the other two roots needed to be a conjugate pair, and then were able to use the sum of roots to find the real part. So what I said over here is quite important, that you had to recognize that you have a complex conjugate for the solutions of this quadratic. The reason being, we were told in the question that the roots can be plotted on an Argand diagram. That tells you that the quadratic has complex roots. And then from that, we could use the sum to find out the real part, i.e. the minus 2. What else was being said? Many diagrams did not show a conjugate pair, so the method to find the imaginary part using the area of the triangle was not always successful. So me drawing a triangle over here on an Argand diagram showing the roots would help to essentially find out the complex part. Those that found values for the real and imaginary part of the roots were able to find the values of P and Q. Okay. Many used the method in the scheme, but some multiplied out z minus 3 lots of z minus the first root lots of z minus the second root successfully. Many who tried the alternative approach by divided successfully by z minus 3 were unable to use the quadratic to any great effect. Drawing a diagram certainly helped with this question. So whenever you see this word Argand diagram, try to use that to basically draw the roots out, okay? So once we found the values of the other roots, it was quite easy to use the product, which is, if I'll go back up this bit, to find the values of P and Q. So overall, a very, very tough question in my opinion. Question number 8. We have to prove by induction, for n being a positive integer, that 5 minus 8, 2 minus 3 to the power of n is equal to 4n plus 1 minus 8n, 2n, and 1 minus 4n. Well, whenever we have a proof by induction question involving matrices, essentially our end goal, we want to show is 4 lots of k plus 1 plus 1, 2 lots of k plus 1 minus 8 lots of k plus 1 and 1 minus 4 lots of k plus 1. Essentially, whenever we see an n on the right hand side, we want to replace that n with k plus 1. So our first typical step in a proof by induction question, so for first part, step 1, our step 1 is our basis step. That's to say that when n equals 1, we can find out the left hand side and the right hand side. So when n equals 1, the left hand side is equal to 5 minus 8, 2 minus 3 to the power of 1, which is 5 minus 8, 2 minus 3. And on the right hand side, for the right hand side, we have 4 times by 1 plus 1, minus 8 times by 1, 2 times by 1, 1 minus 4 times by 1. So we have 5 minus 8, 2 minus 3. And therefore, the left hand side equals the right hand side, so the statement is true for n equals 1. Our second step is our assumption step. So step 2 is the assumption step. And when we talk about the assumption step, and what we are doing over here is we will assume the result is true for n equals k. In other words, when n equals k, on the left hand side we have 5 minus 8, 2 minus 3 to the power of k. On the other side we have 4k plus 1, 2k minus 8k, 1 minus 4k. Okay, and we might use this result later on. And then our inductive step is to try and see what happens when n equals k plus 1. So step 3 is our inductive step, and that's to basically try to see what happens when n equals k plus 1. And when we talk about our inductive step, we substitute in n equals k plus 1 into the left hand side. That's crucial. And then once we do that, we somehow try to get to this bit over here. So we have 5 minus 8, 2 minus 3 to the power of k plus 1. We can use the laws of indices to split this up as 5 minus 8, 2 minus 3 to the power of k. Lots of 5 minus 8, 2 minus 3 to the power of 1. Now, this bit to the power of k, using our step 2, that's 4k plus 1 minus 8k, 2k and 1 minus 4k, and 5 minus 8, 2 minus 3, that's to the power of 1, that's 5 minus 8, 2 minus 3. So now we can use that bit, hopefully successfully. We have 4k plus 1 minus 8k, 2k and 1 minus 4k multiplied by 5 minus 8, 2 minus 3. And our next step is quite straightforward. We just have to multiply these together. 4k plus 1 lots of 5. So we have 4k plus 1 lots of 5 plus minus 8k lots of 2. For the other element, we have 4k plus 1 lots of minus 8 plus minus 8k lots of minus 3. Okay. Sorry, let me just double check this. So we have, just double check the matrix. So we have 4k minus 8 lots. Okay, yeah, that's right. And then for the other element, we have 2k lots of 5 plus 1 minus 4k lots of 2, and then for the final element we have 2k lots of minus 8 plus 1 minus 4k lots of minus 3. Okay, so if we simplify the first element, we have 4k times by 5, which is 20k, then plus 5, then minus 16k. For the other element, we have 4k times by minus 8, which is minus 32k, and then we have 1 times by minus 8, which is minus 8, and then we have here plus 24k, and then here we have 10k plus 2 minus 8k, and then here we have minus 8k minus 3 plus 12k. And if we simplify all this, we have 4k plus 5 minus 8k minus 8, 2k plus 2, and minus 4k plus 3. And if we consider the 4k plus 5, we can rewrite that as 4 lots of k plus 1 plus 1. And obviously 4 times by k gives a 4k, 4 times by 1 plus the 1 gives a 5. Then here we can factorize out a minus 8, so we have minus 8 lots of k plus 1, which gives minus 8k minus 8. Here we have 2 lots of k plus 1, which expands to give 2k plus 2. And here we have 1 minus 4 lots of k plus 1, which gives, well, here we have 1 minus 4k minus 4, which gives minus 4k plus 3. And indeed, that's the bit we wanted to show. So then our final step, step 4, step 4 then would be our conclusion step. We can conclude the following. So obviously with our conclusion step, if true for n equals k, then true for n equals k plus 1, true for n equals 1, and then true for all positive integers. Now for part B, we have to prove by induction for all positive integers that f of n equals 4 to the power of n plus 1 plus 5 lots of 2n minus 1 is divisible by 21. This looks like one of those questions that will give a lot of people problems, but it's actually quite easy. So for the next part, f of n equals 4 to the power of n plus 1 plus 5 to the power of 2n plus 1. Now, if we want to show that this result's divisible by 21, of course we begin with step 1, which is our basis step. We want to show that when n equals 1, f of 1 is divisible by 21. So we have 4 to the power of 1 plus 1 plus 5 lots to the power of 2 lots of 1 plus 1. So we have 4 squared plus 5 to the power of 3 so we have 16. Well, let's just work this out. We have 4 to the power of 1 plus 1 plus 5 to the power of 2 lots of this plus 1. Am I missing something here? I think this should be, well, it's 2n minus 1, sorry. So that was my mistake. So we have 4 squared plus 5 to the power of 1, which is 21. And therefore, we see that 21 is divisible by 21, and therefore the statement is true when n equals 1. So the statement
is true when n equals 1. Step 2. For step 2, that's our assumption step. And with our assumption step, we will assume over here that the result is true when n equals k. In other words, f of k equals 2 to the power of k plus 1 plus 5 to the power of 2k minus 1 is divisible by 21. Step 3. This is our inductive step. And this step is the most complicated, and there's a variety of ways we can do this particular step. The way I'm going to do it, I'm going to express f of k plus 1 in terms of f of k. And we've seen essentially that f of k is divisible by 21. So if we go back to the question, we have f of n equals 4 to the power of n plus 1 plus 5 to the power of 2n minus 1. So when we talk about our inductive step, this one's quite complicated. We have f of k plus 1 equals 4 to the power of k plus 1 plus 1 plus 5 to the power of 2 lots of k plus 1 minus 1. So using the laws of indices, this is the same as 4 to the power of k plus 1 times by 4 to the power of 1. Remember, we add the powers here. And if we expand the top, we have 5 to the power of 2k plus 2 minus 1. And essentially what we want to do over here is, well, if you go back to what f of k is equal to 2 to the power of k plus 1 plus 5 to the power of 2k minus 1. And somehow, with our inductive step, we want to show, firstly, that f of k plus 1 looks something similar to this. So we want some number multiplied by 4 to the power of k plus 1 plus another number multiplied by 5 to the power of 2k minus 1. So the way we can do that is by noticing here 4 to the power of 1, that's just 4. So we have 4 lots of 4 to the power of k plus 1. And then we want a 5 to the power of 2k minus 1. We've still got this 5 to the power of 2 left over. Okay, and remember, adding the powers, we get that. So we have 4 times by 4 to the power of k plus 1 plus 25 lots of 5 to the power of 2k minus 1. And now we would have to work out the difference between f of k plus 1 and f of k. So f of k plus 1 minus f of k plus 1, we've just worked that out to be 4 lots of 4 to the power of k plus 1 plus 25 lots of 5 to the power of 2k minus 1. And then f of k, that f of k is equal to 2 to the power of k plus 1 plus 5 to the power of 2k. Sorry. We have 4 over here. I don't know how I missed that, I'm sorry. We have 4 to the power of k plus 1 plus 5 to the power of 2k minus 1. So we have 4 to the power of k plus 1 plus 5 to the power of 2k minus 1. So if we can simplify this, that'll help. We have 4 lots of 4 to the power of k plus 1 plus 25 lots of 5 to the power of 2k minus 1, minus 4 to the power of k plus 1, minus 5 to the power of 2k minus 1. And if we simplify this, here you'll notice we have 3 lots of 4 to the power of k plus 1, plus 24 lots of 5 to the power of 2k minus 1. And you have to be a bit careful over here. We want to somehow show that this thing, that's an easier way of explaining it. Somehow we want to show that the entire result of f of k plus 1 is divisible by 21. And this 24, if I just write this out, this 24 is the same as 21 plus 3. So we have over here 3 lots of 5 to the power of 2k minus 1 plus 21 lots of 5 to the power of 2k minus 1. So essentially, if I grab the highlighter, 3 plus 21 gives the 24. And now we can factorize out a 3. So we have 3 times by 4 to the power of k plus 1 plus 5 to the power of 2k minus 1 plus 21 lots of 5 to the power of 2k minus 1. And this over here, is f of k. Remember, if you go back, f of k is over here. So what we can say then from here is we have 3 lots of f of k plus 21 lots of 5 to the power of 2k minus 1. In other words, we can say that f of k plus 1 is equal to f of k. So if I take this over to the right hand side, we have f of k plus 3 lots of f of k plus 21 lots of 5 to the power of 2k minus 1. Which we can say in conclusion, f of k plus 1 is equal to 4 lots of f of k plus 21 lots of 5 to the power of 2k minus 1. And we know that f of k is divisible by 21, so 4 lots of something divisible by 21 is also divisible by 21, and 5 to the power of 2k minus 1 multiplied by 21 is divisible by 21. So therefore we have something which is divisible by 21 plus something else which is divisible by 21. The entire thing is divisible by 21. So therefore, in conclusion, if true for n equals k, then true for n equals k plus 1, true for n equals 1, so true for all positive integers. Examiner report wise, mathematical induction is a well-known topic, and through the new specification may introduce some different introduction proofs. The two in this question should have been familiar to students because they're typical examples. Nevertheless, mathematical induction continues to be a topic that confounds many students. Of the two parts, the first part with the matrices was more accessible to students. And this was a standard proof using a 2x2 matrix multiplication, and most students knew the steps well. Some did not show the n equals 1 case clearly and lost a mark. Okay, so if I go back to that part of the question, when they talk about showing clearly, expand the full thing and work the full thing out when n equals 1. Some students made slips in the multiplication of terms and did not write the final matrix in terms of k plus 1. So with these sort of problems, I would advise you to write out what you want to show first and try to get to that. Leaving the examiner to interpret that the final matrix was of the required form. The final statement was usually clear, but some did not make the if true for n equals 1 and n equals k, then etc. clearly enough. So I think the conclusion step
has to be pretty clear. Other errors in the first part include basic algebra errors, and in a small number of cases attempting to find the matrix of k plus 1 by incorrectly using m to the power of k plus m. Remember, we have to multiply the bases. The next part was answered less well. Most students achieved the first 3 marks for showing n equals 1 is true, stating the assumption, and attempting f of k plus 1, but a large number struggled to go any further. Of those that did manage to correctly obtain an expression that contained f of k, the majority went on to achieve full marks, though some that used way 1 or 3 did not find a correct expression for f of k plus 1 alone. All 4 methods were used, with none standing out as being the most successful. So when they talk about that, let's just jump to the mark scheme. So there's 4 ways over here apparently. So we've got the first way, which is the way I did I use this way? I use this way over here. Way 2. Sorry, I used way 2 over here, which made more sense to me. You could also do it in different ways as well, but I think way 2 is the easiest way to do it. Question 9. A mathematical student is modelling the profile of a glass bottle of water. Figure 1 shows a sketch of a central vertical cross-section, over here, of the bottle, A, B, C, D, E, F, G, H, A, of the bottle, with the measurements taken by the student. The horizontal cross-section between CF and DE is a circle of diameter 8 centimeters, and the cross on the horizontal cross-section between BG and AH is a circle of diameter 2 centimeters. So what all this is saying is, over here we have a cylinder at some point, and we might have to use that cylinder. The student thinks that the curve GF could be modelled as a curve with equation y equals ax squared plus b, where x is in between 1 and 4, so that's just this curved bit, and a and b are constants, and O is the fixed origin, as shown in figure 2. We have to find the value of a and b according to the model. Well, over here, when x is equal to 1, the point G, that's equal to 14 plus 4, which is 18. So here we have coordinates 1, 18. And if we consider f, when x is equal to 4, f is equal to 14. So we have 4, 14. So with that being said, we can now substitute in those coordinates into this equation here. So for part A, at the point 1, 18, we have 18 equals a lots of 1 squared plus b. So we have 18 equals a plus b. Call this equation 1. And if we consider the point 4, 14, and substituting that in, we have 14 equals a lots of 4 squared plus b. So we have 14 equals 16a plus b. We'll call this equation 2. And now solving equation 1 and equation 2 simultaneously by subtracting the equations from each other, we see that we have 15a, which is minus 4. A is equal to minus 4 over 15. And when a is equal to minus 4 over 15, we have minus 4 over 15 plus b equals 18. B, we get 274 over 15.
So knowing the values of a and b, we can therefore conclude that y is equal to minus 4 over 15 x squared plus 274 over 15. We'll call this equation 3. Now, for part B, we have to use the model to find the volume of water that the bottle can contain. Now, if we consider this first diagram here, we've got two cylinders. We've got this first cylinder, which we can find the volume of. So we've got this first cylinder, just shade this in, which we can find the volume of. And we've got this second cylinder, which I'll shade in red, which we can also find the volume of. Okay, so let's just shade this in. We've got two cylinders as well. And what we can also do is use a volume of revolution to find the volume of the curved bit over here. Okay, so we've got three different sections, and we can use volume of a revolution by essentially rotating this curved bit, which will give us the volume of the bit shown in green. So first of all, for part B, the volume of the cylinders. Now, the radius of the first cylinder would be half of 2, which is 1, and the radius of the second cylinder, that would be 4. The height of the cylinder is 14, the other one, that's 10. So the volume of the cylinders, we have pi lots of 1 squared lots of 10 plus plus the bit in red, pi, which is pi lots of 4 squared lots of 14. So if we work this out, we get 10 pi plus 224 pi, which is 234 pi. Okay, and we've also got the volume of the curved bit. So the volume of the curved bit, that will equal, we've got the integral from we've got pi lots of the integral from alpha to beta lots of y squared dy. So we're rotating about the y-axis. We can first of all rearrange our equation to find the what x squared is, and then substitute that into here. So this over here should be x squared rather. And then we know our limits to be, if you go back here, 14 to 18. So if we find out what x squared is, we can rearrange for x squared over here. X squared is equal to 1 over 4 lots of 274 minus 15y. So hopefully you guys shouldn't be struggling with that. So we've got our volume, which we'll find in green. We've got pi lots of the integral from 14 to 18 of 1 over 4 lots of 274 minus 15y dy. And if I take out the the quarter, we have pi over 4 lots of the integral from 14 to 18 of 274 minus 15y dy. And it's quite easy to work that out. We have pi over 4 lots of 274y minus 15y squared over 2 between 14 and 18. So if we work out our upper limit, we have 274 lots of 18 minus 15 lots of 18 squared over 2. And our lower limit, we have 274 lots of 14 minus 15 lots of 14 squared over 2. So therefore, working this out, we get pi over 4 lots of 136, which is 34 pi centimeters cubed. Okay? And therefore, the total volume will equal the 234 pi plus the 34 pi. The total volume is 268 pi centimeters cubed. So for part C, we have to state a limitation of the model. So the limitation could be that the measurements that he took may not be accurate. But for part D, the label on the bottle states that the bottle approximately holds 750 centimeters cubed of water. Use this information on your answer to part B to evaluate the model, explaining your reasoning. Well, we've got the following conclusion which I've made. The actual volume in the bottle which we just worked out was 268 pi centimeters cubed, which if you stick that into your calculator, that's 241.9 etc. centimeters cubed. And that's greater than the 750 that's stated on the bottle. Now, this value of 750 makes sense because this 841 tells us the volume of space in the bottle. And it would make sense that the volume of water is less than the volume of space in the bottle because we need some space for air, if that makes sense. So typically when you look at a water bottle, it's not filled up right to the lid. There's some space left, and that space in the water bottle is usually air. And therefore the model makes sense and is suitable. Examiner report wise, question 9, this proved to be a challenging end to the paper. I didn't think it was that hard, but with signs that some students were struggling to finish in time. Although some blank responses may have been due to students simply not knowing where to start. Contextual questions are a necessity on the new specification, so students will have to get used to tackling them. So that's a bit blunt, but okay. Part A did prove accessible to more students, with some degree of progress being made. Many achieved both marks for correct values, though some did make slips in simplification of some terms. A few did not correctly associate the coordinates, but did at least try to engage with the question. I mean, I didn't think, if I go back to the diagram, I didn't think that finding the coordinates were that difficult, but I mean, looking at it, it makes sense. What else could be said? Part B tested the understanding of volumes of revolution in context, and many failed to correctly identify the cylindrical parts of the bottle that were needed to form the overall shape. Many omitted these altogether, while others attempted a single cylinder drawn down the center. Another popular error was the attempt to subtract a cylinder from the solid formed from the rotation of the curve. I didn't think that would be possible, but most were able to form the correct follow-through expression for their answer to part A, but many did not use the correct limits in the context of the question, with 0 and 4 or 1 and 4 being very common choices. There were also many who attempted a volume of revolution about the x-axis who could gain no credit other than for the cylinders if they found them. So I mean looking at the diagram, we're obviously going to rotate about the y-axis. So if it helps, if I draw this on, if I rotate about the x-axis, you'd end up with something like that. And if I rotate about the y-axis, let's do it in a different color, you'd be rotating around here. So what else can be said? Even the integration proved somewhat problematic in that some students did not show they're working. Show you're working, okay? Presumably some students use their calculators to perform definite integration, but it should be emphasized that in questions such as these, full working should be shown, otherwise you can get method marks. Those who did show the working for the integration did acquire the method mark, and those with correct A and B consequently gained the accuracy too. Putting the volumes together successfully was successfully achieved by those who did work out the correct portions that were needed, though some students omitted the pi on the integral. For many, failure to correctly identify the two required cylinders lost the final 2 marks of this part. Part C saw a wide variety of answers, many suitable to access the mark. However, a common response was to state that the bottle may not be full, which did not score as it's not a limitation of the model. Students need to understand that a limitation of the model needs to refer to a feature of the model, such as appropriateness of equation used or aspects that may affect the suitability to be used. So if you go back here, it says over here that somewhere in the question that the student took measurements, so that his measurements may not be entirely accurate. Part D was not answered well. There was perhaps some confusion as to the difference between a limitation and the evaluation of the model, with some students again referring to a limitation here. So essentially you've swapped the answers. It was important that a comparison be made here, and there was no need to offer a reason why it may or may not have been appropriate, but simply to have drawn a conclusion from the comparison as to whether the model is suitable or not. An appreciation that the label should be an underestimate of the true volume, so that the bottle could contain this amount with spare room. So that's exactly what I said. It was not shown by many students. Those students who answered correctly here mainly focused on how far out, with specific reference to greater than or less than, their value was from the stated volume, and hence made an evaluation of the model. So if we quickly take a look at the mark scheme for this question, see what the mark scheme says. The mark scheme basically tells us that we need a comparison of the 750 with our value and a conclusion based on that comparison. So if your answer is less than 750, then you need to conclude that it's not a good model. But if your answer is more than 750, which is what we got, we need to make a sensible comment that's consistent with that value. So if there's no addition, okay, yeah, so over here makes an assessment of the model with a reason with no contradictory statements. So here, with these sorts of modelling questions, you have to think about common sense in real life situations. So anyway, that's the end of the paper. Don't forget to like, share and subscribe. I do hope that this video is helpful. Hopefully I'll see you on the next paper.